Okay, so before I start the practice exam stuff, I wanted to do Klaus's Clapeyron question. And I forgot if this class, I think this class did a little better generally, but on the quiz, the last question I talked about, well, what units do you need to have on your x and y axis, and how do you calculate the delta H? I just want to go through from scratch how you would do any kind of problem based on the Klaus's Clapeyron equation. So this is from the homework. I'll just do it, and if you know it already, that's fine, but I'm going to do it for people that don't understand. So what we have here is a series of temperatures that someone has taken a liquid, and that's a really low temperature, so that makes sense for something like nitrogen. So nitrogen is not a gas anymore, it's a liquid at these temperatures, but the liquid itself is generating vapor. It's not boiling, but it's evaporating, just like water does. And the vapor pressure of the gas that it's generating is, these numbers. As you increase the temperature, the vapor pressure goes up. And you can see that the vapor pressure goes above atmospheric pressure, somewhere between here and here. So atmospheric pressure is 760 torr, 760 millimeters of mercury. So that basically tells you that the boiling point for liquid nitrogen is somewhere between 75 and 80. Okay. So I'm going to just show you what you can do with this. I've got it already on a spreadsheet. Those are those numbers. The T is off the screen a little bit, but it's on the board. So that's temperature and pressure. If you plot those, just to show you what it looks like. Oop, my mouse pad button stuck. There we go. Insert scatter plot, just the points. This is a little bit big. Let me shrink it. Yeah, scatter plot, that's always the plot we're going to be using. Never getting connected the dots, nothing like that. So you can kind of see it's curved. It's not linear, it's curvy. This is something you can fit. Like Excel will fit curved lines to a series of points. The thing is, when your data is not perfect, it's very difficult to fit a curved line. And it's hard to tell how well the curved line fits. Like, maybe it's not fitting because you're using the wrong curved equation. Is it a squared? Is it a cubed? Is it something else? So it's always easy to fit straight lines. You can visually see it fits really well or it's not, and we have statistics that'll tell you how well it fits. So in our case, we're going to be using the Klaus's Clapeyron equation, but this is that vapor pressure curve, right? So we have temperature over here, we have pressure here. As the temperature goes up, the vapor pressure goes up. But the Klaus's Clapeyron equation is the log of vapor pressure is equal to minus delta H vapor pressure over R times 1 over T plus the natural log of beta. And this is basically saying if I plot this on my y-axis and this on my x-axis, then I will get a straight line where this is my slope, or m, and this is my y-intercept. So we have to transform this data. I am going to instead now do 1 over the temperature. And in Excel, you can just do equals 1 over, equals 1 divided by this number. And I can copy it all the way down. So that's 1 over this temperature. And then I'm going to do natural log of the vapor pressure. So equals ln of this number. And I can copy that down. So instead of now plotting this, these 2 points, I'm going to plot these 2 points. And so I think I can do this as a shortcut. Let's see.
What did you put for the equation in the C column again?
Oh, it's just 1 divided by the temperature value. So 1 over. Now, this I can't ask you to do on an exam because can't do this. But from here on, once you get the graph, That's, well, not yet. We haven't gotten the graph, but if you're here on, that's what you could do. That's what we did in the quiz. All right, let me just redo this. So now I'm going to plot, insert, actually, let me highlight this first. Highlight, insert scatter plot. And you can see that's pretty straight. Let's see how straight it is. Let's add a trend line. Right click, add trend line. And I'm going to change, oops, down here, the display equation on chart, and I'm going to display the r² value as well. Done. So there it is. That's the equation of our straight line. We've got a slope, we've got a y-intercept, and the r² value is just an indicator of how straight, how well the line fits the points. The closer it is to 1, the more perfect the fit is. So that's pretty much perfect data. Normally your data is not that perfect, but so there it is. There's our slope, -711.98. Now this doesn't tell you like units. It doesn't tell you what the x and y mean. You have to know what it means. So when you rewrite, like typically we'll actually rewrite that into the form of the Clapeyron equation. So you'd rewrite it as log of the vapor pressure is equal to that number. The units for the slope are going to be in Kelvin, and then times 1/t plus that, and the units of this is going to be unitless, no units. But anyway, the slope is equal to this thing right here. This number is equal to that. And I know what R is. R is the gas constant. So I'm going to replace R with the actual gas constant. Joules per mole per Kelvin. And then do some algebra. So I think some people made mistakes with the algebra. If I want to isolate this. This is already in the numerator. So I'm going to multiply both sides by this number, 8.314, to get rid of this on this side. And then it'll be on this side. So I end up basically delta H vaporization is equal to, the negatives will cancel out. I'm just going to not write those at all. 711.98 Kelvin times 8.314 joules per mole per Kelvin. Notice that the kelvins cancel out, numerator, denominator, and you're left with joules per mole. So if we do this, 711.98 times 8.314, I get 5,919 joules per mole. We normally see enthalpies in kilojoules per mole, though, not joules per mole. So typically we'll ask you to convert to kilojoules. So I want kilojoules. I want to get rid of joules. 1 kilojoule is 1,000 joules, or 10 to the 3. So this becomes 5.9, I don't know how many sig figs it's going to be, kilojoules per mole. So that is the enthalpy of vaporization for liquid nitrogen. On the quiz, we did ammonia, and I think it was like 30 something, maybe 20 something, 24.
27 or something.
Okay, it was a lot higher. And that should make sense in your head, because what does an enthalpy of vaporization tell you? It's how much energy is needed to convert the liquid into a gas. And so something that has very few intermolecular forces, like liquid nitrogen, which is just nonpolar, it's very small atoms, or the molecule is really small, is going to have very weak interactions with its neighbors. So it doesn't take much energy at all to turn it into a gas, whereas ammonia, which has hydrogen bonding, it's going to take a lot of energy to turn it into gas. So that's it. That's the basis of, that's what you guys have to learn about this equation. The only other thing you might have to do is find beta, which we can. So the log of beta is equal to this y-intercept, 15.833. And to get rid of this natural log, we'll do e to the both sides. And what happens with this is the beta comes out, and it becomes beta is equal to e to the 15.833. And you can put that in your calculator, you get a big number. So it's not the EE thing that's in your calculator that we've been using for times 10 to the power of. It's the E Euler's number. 7.5 times 10 to the 7? 7. And
No
it's,
units.
I think let me think. I think technically the beta will have the units of what your pressures were originally in. But it actually doesn't matter in our particular case, because once we do the natural log of it, the units disappear.
Alright, so the only reason we knew B was because of this graph
Yes.
and it did it for us. Will we be doing any variation of this where we're finding beta, like how far do we need to know how
Well,
to do
so
this?
on the quiz, I just gave you the slope.
Right.
So you would need a y-intercept in order to calculate beta. So maybe if I gave you the graph itself, and I said, here's the graph, give me this and this. And you should be able to figure it out from that. But yeah, you need a y-intercept to calculate beta. There's no way around that. Okay. And I think that's, like, the equation itself looks nasty. That's it. That's all you're going to have to do. The only other scenario I think that you guys maybe saw in the homework, which I am not going to do. Yeah, which I'm not going to do in the exam, is I think maybe there was a different form of the Clausius-Klaproth equation where there was two pressures and two temperatures. You guys see that one? Yeah. So it was like log of P1 over P2 is equal to minus delta H over R. And this is the one I can't remember if it's T1 or T2 first. Like that. And the idea was, if I've got delta H vaporization, I can plug in one set of pressures and temperatures, and I can find what the other pressure at a different temperature is. I'm not going to do that, but probably you saw that number. Those kind of questions rely on like knowing. So they give you the delta H, okay? So it's some number. They give it to you. And then they say, well, what is the vapor pressure at something like 298 Kelvin? And you'd be like, well, where's my other set of data? Where's my T2 and P2 or P1 and T1? Well, they also usually give you a boiling point. The boiling point was 330 Kelvin, something like that. Well, this is where you come up with, well, what's the definition of boiling? What is happening when you get to boiling? Well, when you get to boiling, the vapor pressure has now equaled atmospheric pressure. So the idea is, well, your T2 is going to be 330. The P2 has to be 760 torr, or 1 atmosphere, either way. Right? That's the homework. But so I'm not going to give you that question on the exam. Okay? We'll stick with stuff like this and stuff we practiced. Okay. Any questions about this? Anything else in the quiz? We can go over real quickly. If not, we'll just go straight to this. And I did mention that there's a few errors here and there on the key. So let me know. I haven't fixed them yet, but we did run into them yesterday. So order electrostatic forces from weakest to strongest. So we're using the word electrostatic forces, not IMFs. An electrostatic force is any force that involves charges. So that does include ionic bonds, because you have full negative and full positive charges. But all of the IMFs are electrostatic forces as well, because they are partial charges. That's what causes the attraction. So in this case, London dispersion are the weakest. Ionic are going to be the strongest. That's a full plus, or even more than that, +2, -1, -2, full charges. Everything else in between is partial charges. And so we know from IMF, London dispersion, dipole-dipole, hydrogen bonding. So between hydrogen bonding and ionic, you could include also ion dipole forces when you mix ions and regular dipoles. Okay. Okay. So which of the species below would you expect to show the most hydrogen bonding? This is a little bit tricky because when you look at this, well, the single HF bond has the strongest dipole moment. The bond, but not the molecule. So OH, one OH bond is weaker, has a weaker dipole moment than one HF bond, but OH has two OH bonds. And then NH3 is weaker, so the NH bond is weaker than all of them, but it's got three of them. So how do we know which is the strongest? Well, go by boiling points. HF is actually a gas at room temperature, if you didn't realize. Ammonia is also a gas at room temperature, whereas water is a liquid. So all of a sudden, it's pretty clear water has the strongest it has the strongest attraction, so it's got the most hydrogen bonding. We've talked about water being unique. It's just so strong. So the NH dipole moment is a particularly weak form of hydrogen bonding, and three of them still doesn't quite get you to the level that water does. Okay. Okay, so water is it. And you can just go by regular properties. It's got the highest boiling point of them all. Hopefully you can ignore the CH4. That doesn't belong at all. Okay, so these five different compounds. Hopefully you remember that, the boiling point starts to go down as you go from heavy compounds to lighter compounds, but then it goes back up when you get to ammonia, and hopefully you understand that that's because of hydrogen bonding. All right, the ammonia has this special kind of dipole attraction called hydrogen bonding. It's just a much stronger dipole moment. And that's why it doesn't follow the trend. So what types of intermolecular forces exist between HI and H2S? So be careful with these. You kind of have to draw things sometimes. HI is pretty easy. That's HI. It's just one bond. And although iodine is not really super electronegative, it's going to be a somewhat electronegative. So there's a small dipole moment between H and I, tiny. But H2S, if you do the Lewis structure, is bent, right? And that's because it's got two lone pairs on it. This is a bent shape. The SH bond is kind of polar, but it's not like CO2. They don't cancel each other out. They point overall in this direction. So this has got a pretty decent dipole moment. So does this. And so we're going to do dipole-dipole forces. That would be the strongest IMF between them. But this is not asking for the strongest, it's asking for all of them. Everything does dispersion forces, everything. So dipole, and dispersion forces. Okay. No hydrogen bonding. There's no NH, no OH, no FH bond. C12H26, they're held together. Well, you could draw that out if you like. You could recognize there's no O's, there's no N's, there's no very electronegative atoms. This is an alkane. It follows the formula of an alkane. The number of carbons times 2 plus 2. So yeah, it's just hydrogen bonding. Or not hydrogen bonding, the opposite. Dispersion forces, London dispersion forces. So E is the only thing that is holding two of these molecules near each other, okay? It is a liquid. So they're pretty strong dispersion forces, but that's it. This is another one. If you can see it from this structure, the condensed structural formula, great. If you can't, draw it out. So the parentheses, CH3, there's 2 of these CH3s. What's next is a nitrogen. So the 2 CH3s are stuck on the nitrogen. And then on the other side, there's an H. If you really want to do the Lewis structure, there should be a lone pair on the nitrogen, but that's not necessary. But here you can see NH bond immediately, hydrogen bonding. This does hydrogen bonding with neighbors. And it's the predominant intermolecular force, so hydrogen bonding. Okay. 7, argon has a higher melting point than neon because stronger dipole-dipole interaction. There's no dipole. Neon and argon are both atomic gases. There's no polar bond. There's no bond. So they're just neutral atoms floating around. There's no hydrogen, so there's no hydrogen bonding. Stronger dispersion forces in argon. So why stronger dispersion forces in argon? That's the answer. Why does argon have stronger dispersion forces than neon?
Because it has a larger molecular mass than.
That is, you're technically right. But the thing is, that's not the why. So yes, higher molar masses correlate to stronger IMFs. But yeah,
It has like another ring of electrons, so it's more polarizable.
yes. So the outer electrons in argon are more polarizable because those electrons are further away from the nucleus. They're in shell 3. They're more loosely held, and meaning they're more polarizable. They're more easily distorted. So they do stronger dispersion forces for that reason. But yeah, molar mass correlates with that. So that's why we look at molar mass. So yeah, good. So C is the answer anyway. Based on molecular mass and dipole moment, which would have the highest boiling point? So don't just see, oh, there's an HO in here. That's hydrogen bonding. That's the strongest. Because that's not an OH. This is typical for how we show an aldehyde. And it's even written here. This is an aldehyde, acetaldehyde. And an aldehyde is drawn like this. So more carbons, but on the end it's this. There's a dipole moment there, but that's it. There's no hydrogen bonding. There's no OH bond. So ignore all that because they're literally giving you the measurements of the dipole moment. And the one with the highest dipole moment is going to have the strongest IMFs, and that's going to have the strongest, or highest boiling point. Yes?
So if they didn't give us the table, we probably should use just like drawing the Lewis structures, because if you didn't draw it, then I would think that it is.
You should draw the Lewis structures and see if there's any hydrogen bonding, and I would go with that first, and if not, then go with the most. So acetonitrile is a weird one. I go with the most electronegative, and the reason I say acetonitrile is a weird one, nitrogen is not that. You would think that C double bond O is stronger than a CN. But it's C triple bond N, and for some reason that is like there's a really large dipole moment difference. We haven't really studied this bond, like that's not one of the functional groups we talked about. So it's not like I would give you this out of the blue. But given that we have the dipole moment here, that's much more clear, okay? So when it comes to drawing things out and looking at what's stronger, we're gonna stick with the functional groups we've studied, okay? Which of the two molecules would have the lower melting point? Who knows? Lower melting point. So A. So these have the same molar mass. The one that is more bunched up and takes a smaller surface area is going to have the weakest intermolecular forces, and so it's going to have the lowest boiling point. This is more branched. So there's 2 carbon branches. So if that's the long chain, 4 carbons long, There's a branch here and a branch here. However you think of where the carbon chain is, 4 here, branch here, it doesn't matter, it's the same. But here there's 1, 2, 3, 4, 5 carbons in a chain, 1 branch. It's less branched. It's going to have stronger IMFs. It's more stretched out. There's more surface area for it to interact with other molecules of the same type. So it's going to have a higher boiling point. So A is the lowest boiling point. Not by a lot, but by a little bit. Hydrogen bonds account for which of the following observations? So this is really understanding what we mean by hydrogen bonds. We're not talking about the covalent bond between hydrogen and something else. We're talking about the interactions that a strong dipole moment involving hydrogen and oxygen, hydrogen and nitrogen, hydrogen fluorine make with neighbors. So hydrogen naturally exists as diatomic. That's not it. That has nothing to do with hydrogen bonding. It's easily combustible with oxygen. That's not it either. Hydrogen bonding is a physical property. We're not talking about chemical properties, which is what this is talking about. Water molecules are bent. Well, it's true, but that has nothing to do with hydrogen bonding either. Sort of. Air is more dense than hydrogen gas. That's true too, but there's no hydrogen bonding in air. Air is just O2 and N2, mostly. There's a little bit of water in there, but that's it. That's not really the majority of it. For its molar mass, water has a high boiling point. So that's it. The fact that water does hydrogen bonding is what causes it to have a really, really high boiling point. Okay? Okay. These are all true, though. Only one of them is relevant to the question. Yes?
So I know, like, water has a high. Oh, so it is because of the molar mass that it has a really high one.
Well, no, it's got a really low molar mass. It's
Yeah.
only 18. If we compare that to methane, ammonia is 17, which is a gas at room temperature. Methane's a gas, and their molar masses are similar.
Yeah.
So it's the hydrogen bonding in water that makes it a liquid instead of a gas.
Then why does it say for its molar mass? Oh, it's
It's
okay,
contrary to its molar, contrary to the fact that it has a low molar mass. Yeah. Yeah. Okay. So on a relative basis, the weaker the IMFs in a substance, the greater its heat of vaporization. No, the greater the weaker the molar mass is, the easier it is to vaporize it. So it would have a lower heat of vaporization. The more it deviates from ideal gas behavior. So what is ideal gas behavior? That is no IMFs, no volume. So it would get better. That wouldn't deviate. Deviate meaning become more real-like. But no, that's the opposite. The greater its vapor pressure. That is true. So this is the one that goes opposite with IMFs. So the weaker the IMFs, the more vapor you're going to be able to generate. So the more vapor pressure you'll have. Right? The stronger the IMFs, the more the liquid stays a liquid. And it doesn't want to make gas because they stay stuck together. So C is it.
The only one with the inverse relationship.
Yes. We've talked about all the other kind of properties like surface tension and viscosity and capillary action. Those increase with IMFs, but vapor pressure goes down with IMFs. Yeah. Okay. Molecules in a sample of solid SO2 are attracted to each other by combination of what? So this is one that is useful to draw. And I'm going to do it from scratch just in case you've forgotten how to do Lewis structures. Just in case. So SO2, to do a Lewis structure, we're going to count valence electrons. Sulfur has got 6. It's in group 6. Oxygen has 6 as well. So 6 from the sulfur, 6 from each oxygen. There's 2 of them. That's 18 total valence electrons.
Wait, isn't oxygen 6? Oh, it's 6 valence.
6 valence electrons, yeah. It's got 8 total, but 6 in the outer shell. Okay. Then we'll do a skeletal structure. We put the least electronegative element in the center. We surround it with the outer atoms, the 2 oxygens, and we make a single bond between the outer atoms and the central atom. Each bond represents 2 electrons. So I've got drawn in 4 electrons, 2, 4. I'm going to subtract that from the pool of electrons that need to show up in the structure. And then I'm going to do the octet rule for the outer atoms. So this oxygen needs 8 total. It's got 2 next to it. I need 6 more. This oxygen needs 8 total. It's got 2 next to it. I'm going to put 6 more. And I've got 2 electrons left, so we'll do the octet rule for the central atom now. This sulfur has 1, 2, 3, 4 electrons next to it. It needs 8. Well, I've only got 2 left, so I'll draw those 2. I've got no electrons left, but this does not satisfy the octet rule, so then I'll share. I will take a pair from the outer atoms and share it with the central atom. And which one you take doesn't matter, so let's take these 2. We're going to move them here instead. There we go. By the way, that indicates resonance, the fact that you could have done it from either side. But that's it. That's a Lewis structure. And then you count 1, 2, 3 groups of electrons around that central atom. So each lone pair counts as a group. Each bond cluster counts as a group. So 3 groups means that the electron geometry is called trigonal planar. But the molecular geometry is based on how many of those groups have an atom attached to them. So there's only 2 atoms here. So if I draw these electrons in trigonal planar, that's the shape. But only, there's atoms here only. That shape is bent. So what does that tell me? Well, there is a dipole moment going this way. There's a dipole moment going this way. Oxygen is more electronegative than sulfur. And these do not cancel each other out. They both point downwards. And this is the way I drew it, at least. So there is an overall dipole moment going this way. All that is to show that this is polar. Okay? I mean, until you're used to seeing this, and you know what it looks like, you could end up with like CO2. CO2, while it has 2 atoms, like sulfur has 2 atoms, 2 oxygens, these are linear. And so the dipole moments point in opposite directions. They cancel each other out. This is a nonpolar molecule. So this doesn't do dipole-dipole interactions. This only does London dispersion forces. So that's why you have to kind of understand the shape. So this is polar. So it does dipole-dipole interactions, no hydrogen bonding. But combination. So what are all IMFs? Well, in addition to the dipole-dipole, there's London dispersion forces. So D, London dispersion forces and dipole-dipole interactions. Yes?
I remember a couple mastering chemistries when we were like doing that stuff.
Uh-huh.
It would ask like, what is all the forces in this? And I thought like London forces for all of them. So I would put that and the other ones, and it said like, sometimes it would be like, no, it doesn't have London or something.
It should always have London if it's asking for all of them. If it's only asking for the strongest one, then it depends. But I'm not sure what is happening. But they should all do dispersion forces. Because dispersion, yeah, they should all do that. Yeah. To an extent, I guess. I guess you could get nitpicky and like take an inorganic compound like that and say, there's really only polar bonds in there and that's it. So there's no need to do dispersion forces, but I don't know. I think this London dispersion forces is valid for everything, I think. Okay, which of these would you expect to have the highest vapor pressure at room temperature? So we're given boiling point data. So we know that boiling point data correlates with strong IMFs. So the ethylene glycol is the strongest. The diethyl ether is the weakest IMFs. So the weakest IMFs will give us the most vapor. Will have the highest vapor pressure. And so that's diethyl ether is going to have the highest vapor pressure at room temperature. At any temperature, it'll be the highest in any case. Okay. A liquid placed in a closed container will evaporate until equilibrium is reached. at equilibrium, which of the statements of A through D is not true? The partial pressure exerted by the vapor molecules is called the vapor pressure of the liquid. That's true. So when we talk about vapor pressure, that's literally how many, it correlates to the amount of gas particles there are, which is a partial pressure, now that we've understood gas laws. Liquid molecules are still evaporating. That's true as well. So even though the amounts won't change anymore once it reaches equilibrium, there's at the molecular level, liquid is still turning into gas, gas is still turning back into liquid. It's just happening at the same rate, so the numbers never change. And that's where C comes in. The number of vapor molecules remains essentially constant. Yes, the number remains the same, but the actual individual molecules that are a gas versus the liquid, those are changing constantly. The boundary between liquid and vapor disappears. That's the bad one. So that is only happening in supercritical fluids, right? We saw a video of the CO2 one. That's a weird condition. That's not normal liquid, okay? So that is not going to happen. Okay. The normal boiling point of liquid X is less than that of Y, which is less than that of Z, which of the following is the correct order of increasing vapor pressure of three liquids. All right, so that's the same idea. Z is got the highest IMFs, X has got the weakest IMFs. So Z with the highest IMFs is going to have the smallest vapor pressure. So it's B. Z, then Y, then X. So Z is going to have the lowest vapor pressure, X is going to have the highest vapor pressure. All right, 16. This one is a combination of IMFs and kind of just a little common sense stuff we've learned from Lab 2. So here you've got some molecular compounds, right? Motor oil, ammonia, water. And, you can kind of rate those, sort of. But besides these molecular compounds, we've got atomic ones here. These molecular compounds, we've got this thing. This is ionic. And this goes back to Lab 2. Ionic solids, or ionic compounds have really high melting points. Always higher than molecular compounds do. Almost always higher. So that's it, chalk. I mean, you've seen chalk. You know what chalk looks like. It's a solid. So it's going to be hard to boil it and much less melt it. So it's A. Okay. Ionic compounds are just stronger than anything. So when a solid iodine sublimes, what forces must be overcome? Well, iodine is I2, so it's just two I's stuck together in a covalent bond. This is nonpolar. So this molecule, when it's together with other iodine molecules, they're held together with dispersion forces. That's it. No polar bonds, nothing. So C, that's it. They happen to be really strong, though, because it's a solid room temperature. Iodine is way down at the periodic table, very, very polarizable atoms. Those electrons on the outside are really distortable. Okay, 18 is another throwback to Lab 2. And I encourage you to go back to that table and look at that table and make sure that makes sense, where the properties of the different solids. So we've got CCO2, C6H12O6. That's actually glucose, or something similar to that. But it's molecular. Calcium carbide is the other compound. And if you didn't know what it's called, that's fine. It's a metal with a nonmetal. That's an ionic compound. Typically what we think of as an ionic compound, at least. So here's where you kind of have to use your knowledge. C is not C atoms. It's not like individual atoms. C, the natural state of carbon, you could think of graphite or diamond, either one. That's a covalent network. Both of them are covalent networks, which typically have the highest melting points of any compounds. Okay, covalent networks are always the highest. Then come ionic compounds. Then come metals. Then come molecular compounds. Okay, So in terms of lowest to highest, carbon is going to be the highest, whether it's diamond or graphite. Then comes the ionic compound, calcium carbide. Then comes the molecular compounds. And this one, if you didn't know what it looked like, I think all you have to say is, well, compared to this one, CO2, I just drew it up here, is nonpolar. It's got polar bonds in it, but it's nonpolar because those polar bonds cancel each other out in terms of there's no positive or negative side to this molecule. This thing is complex enough that it's probably got some polar bonds in it. If you've done any bio, maybe you've seen the structure of this. It's got a bunch of OHs sticking off of it. But the fact that it's got a bunch of oxygen in it, most likely polar, somewhere. In fact, this does hydrogen bonding, so it's pretty good. So this is the order, okay? D. And if it really is something you have no idea what it should look like and you're not sure, ask me during the exam, and I will try to give you a hint if I can. When a small amount of heat is added to a pure liquid that is just starting to boil, what happens? So this is the throwback to the heating curve. If it's already starting to boil, adding more heat will not change the temperature. All it will do is cause more liquid to boil. So any extra heat you add, any extra energy you add is going to convert more liquid into gas.
So I've seen some heating curves that show the standard, but then it has like a little line up from the boiling point.
So something like that?
Yeah, and then
This part here?
go back over to boiling point. It has a line extending up just a smidge, and it says
Oh, it's got a-
superheated or something.
Oh, well,
I've
that's-
seen some like
okay.
that.
That is a weird state, and I think, so we didn't cover that specifically, but what's happening there is you can actually add more energy than it normally would absorb, and it won't boil. Boiling, like the initiation of boiling requires a defect, so that's why we add. So if you ever boil anything in a microwave, you usually want to add something like a wooden spoon or something, not a metal spoon, but like if you boil something in a Pyrex dish in a microwave, you want to add something to it that will be places for the boiling to initiate, a scratch, a sharp edge, because Pyrex glass is super smooth, unlike metal pans, which have like lots of scratches in them. When you put them on the stove, things boil pretty easily. But when the surface is really, really smooth, the place where bubbles start to form, they call them nucleation sites. You need like rough edges, defects, scratches, and stuff like that. And that's otherwise you'll get to the superheated stage. And so in a microwave, if you just boil something in a really clean Pyrex glass, and it's like clean water, you can heat it past the boiling point, and then when you pull it out, and then you put something in it, it will just explode as it instantly boils. It's very, very dangerous. They've shown MythBuster stuff with that. It's real. But that's an unusual state.
Okay.
So normally flat like that.
We open it. It does.
But in that case, if it's just starting to boil, then it's not superheating.
Right.
It's literally in the first stages of that flat area.
Okay.
Yeah. Okay. Okay. Yeah, you can do that with freezing too, where you cool water down, or anything down below its freezing point, and it'll stay liquid. And then there'll be like a little clicker thing inside, and you click it, and it creates an instantaneous like scratch or kind of defect where the crystallization immediately starts, and the whole thing turns into a solid. And the liquid to solid transition releases a bunch of heat, and it's a heating pack.
Oh yeah.
You've seen those? So yeah, and you recharge them, you put them in the microwave, you turn them back in a liquid, and then you let them cool down, and they'll stay liquid until you click something inside, and then it'll suddenly freeze. And that freezing releases energy in it. It's hot, yeah. right? So freezing is an exothermic process, releases heat. Anyways, funny things you can do with that. Okay. Yeah. I think the disposable heating packs are the rage now. That I haven't seen one of those rechargeable ones in a while. You want to purify a sample of X, collected at 1 atmosphere pressure, and it's currently at this temperature, but you want to sublime it. So it's currently in solid form. That's solid, that's liquid, that's gas. How would you sublime it? Well, you're going to have to bring the pressure down so that you can cross this line, the boundary between solid and gas. So we have to bring the pressure down. Then we can increase the temperature, and it will go from solid to gas directly. This is a very common thing in organic chemistry. To purify something, you'll have a beaker of your garbagey chemical that you've made that's full of other contaminants. You put something on top of it that has ice in it, and then you heat the bottom, maybe sometimes at low pressure. Your solid will turn into gas, and then when it hits the cool surface, because it's cool because there's ice in the beaker above it, it kind of solidifies, makes crystals, and you can scrape them off, and you get purified stuff. So in this case, the answer is C. You have to lower to 1/2 atmosphere pressure. Then you increase the temperature, and you can sublime it. You can turn it to a gas directly. Okay. At 25C and 1 atmosphere, X will exist at, so there's 25, there's 1 atmosphere. It's going to be a liquid. It's right in here. It's a liquid. The normal boiling point of X is most likely. So boiling points and freezing points, or melting points, are all measured at standard atmospheric pressure. You can change the boiling point by having any pressure you want. So we have to set a standard. That's 1 atmosphere. That's the pressure we like. So we look at 1 atmosphere, and we look to see, well, where do we get to this liquid gas boundary? Right there. Somewhere like 48, 47. There you go, B. 47 degrees C. That's the boiling point. How will the melting point change with increased pressure? So here is the melting point at standard atmospheric pressure. It's about 19, 20. If I increase the pressure, oh, look, the melting point has increased. So the melting point increases if I increase the pressure. All right, 24 is the same as before. At 25 degrees and 1 atmosphere, what is it? 25, 1 atmosphere right there, that's a liquid. If it's above this point, it could be a supercritical fluid, but we're not going to get into that. At least not. It'll be clear if it's going to be supercritical. When the phase diagram for a substance has a solid liquid phase boundary and it has a negative slope, it leans to the left. The substance what? So not that graph. That graph has a positive slope for the solid liquid boundary. What they're talking about is,
So like water.
yep, it goes that way. So what happens is can go from solid to liquid with a within a small temperature range via the application of pressure. Yeah, so let's say you've got ice right here, whatever the temperature and whatever the pressure are. If I increase the pressure, it suddenly melts, turns into a liquid. That's pretty unique to water. Maybe something else, I can't remember. It's pretty rare though. So yeah, A, it can go from solid to liquid via the application of pressure. That's it. None of the others should
Is that
fit.
only for water?
This is the only one we've covered, yes.
Is anything that has a negative slope from solid to liquid also working? Like, or can that be something else too?
If say
Is like the only thing that's gonna have a negative slope water?
for us, yes. Yep. I could give you a problem with the negative slope. I'll show it to you, and I'll say this is a new thing, but you're not gonna say, oh, what is it? You won't know it. So, okay. Let's skip this one. I think this one's not too well. Actually, no, this one's okay. Choose the correct statement about this diagram. So, the diagram is qualitatively correct for water. Well, we know water has a negative slope for the solid-liquid boundary, so it can't be that. This one has a positive one. The diagram shows that the melting point of the solid increases with increasing pressure. Yeah, so here's the melting point at regular pressures. If I increase the pressure, the melting point increases. That's it. B. Let's look at the other ones here. The C, the diagram shows the triple point above 1 atmosphere. So there's the triple point. It is below 1 atmosphere. And D, the diagram could represent the phase diagram of CO2.
It has the same shape, except for the little weird angle on the gas line.
Well, yeah, it does have the same shape, but what do we know about CO2, like how it behaves? If I have dry ice, does it ever liquefy? What does it do at regular pressures? It sublimes immediately, which at 1 atmosphere, this is showing a solid would liquefy first, then turn into gas. So CO2's triple point is above 1 atmosphere, yeah. Yep. All right. So 27 is one that I will not give you because we didn't talk about how vapor pressures are related to a phase diagram. It is D, but we're not going to cover that, so we'll skip this one, okay? It's kind of hard to get into why. So 28. So skip 27. 28. So we have a more unusual phase diagram, 2 different solid regions. The system has 2 triple points, yeah? A triple point is any 3 phases can exist at one time. Doesn't matter if it's solid, liquid, gas, or solid, liquid, or whatever. So the 1, 2. By the way, what's a little bit confusing are the solid marker lines. This is just like a guide that tells you what these numbers are. The actual boundaries are these sloped lines. So just don't get confused with the little marker lines. Under atmospheric conditions, sulfur does not sublime. Yeah. You're going from solid to liquid to gas. There's no solid to gas. So that's it. Well, that's true, I should say. It's not incorrect. At pressures close to 1 atmosphere, rhombic sulfur can be in stable equilibrium with liquid sulfur. So there's rhombic sulfur, the SR. There's liquid sulfur. There's no boundary between them. So that if there's no boundary between them, there's no equilibrium between them at all. So that's incorrect. C, there's no stable equilibrium between rhombic sulfur and liquid sulfur. Okay. This one has incorrect numbers in it. So I did this one, and I don't know if I should do this one, because it's exactly the same as what we did here. You're plugging in the slope, and then you're solving for delta H. And when you solve for the delta H on this one, I think it's 36 or something like that.
Yes.
All right, good. So it's none of these, even though the key says I think the key says D.
It does.
The numbers are wrong. I don't know which got changed, but yeah, the numbers are wrong. Sorry about that. So that's why it's highlighted. I gotta fix that.
Well, none of these is an answer.
True.
Oh, but the key was.
The key is wrong too, yeah.
Okay.
All right,
What did you answer was?
what's that?
What did you say the answer was?
36?
35.605.
There you go. Okay. I like 30. It's really simple, but it's like the perfect simple gas law question because you have to think about what goes where. So body temperature is 308 Kelvin. On a cold day, we've got this volume of air at 270, a different temperature, and they're breathing into a lung that has a 2-liter capacity. How much air do you need to breathe in to fill your lungs? So first, if you think about what's changing, temperature is changing, volume is changing. This is a state change problem, so we're going to be using one of those gas laws. In fact, this is a Charles law problem. We're going to be using V1 over T1 is equal to V2 over T2. Now, let's really define what we're starting with and what we're ending with, and that makes the problem easier. We're starting with air on a cold day. So the air at a cold day, temperature 1, is 273 Kelvin. And we're trying to find, well, how much of that air do we need to breathe in? That's the question. What is V1? So after we breathe it in, what happens to it? The air heats up. It reaches body temperature, 308 Kelvin. And it's going to fill the volume of your lungs, which is 2 liters. Now, you could swap these if you want. You could say this is T1 or T2 and V2, and this is T1 and V1. That's fine. But you need to make sure you match the pairs correctly, okay? So we're going to solve for V1. And to solve for V1, I'm going to isolate it. It's already in the numerator, so I'm going to move T1 over to the other side. And I can do that by multiplying both sides by T1. That way T1 cancels. So V1 is equal to V2 T1 over T2. So V2 is 2 liters. T1 is 273 Kelvin. And T2 is 308 Kelvin. And if you do the math, you get 1.77. So you breathe in less air, volume-wise, and it expands to fill your lungs because it gets warmer. And that makes sense. As you heat up the air, it expands. Okay? So, this is one where you have to think a little bit. How do you fill in the spaces?
The
Yeah.
practice exam doesn't have the gas laws on there. Are we going to have to memorize all those?
Let me see what's on there. Ooh, yeah, you're right. So.
Just remember, you can always get them from the ideal gas law.
Well, I was going to say that too, but let's. I'm going to try to remember to give you this. So P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. I'll try to remember to put that on there. And this can be used for everything because for Charles's law, at least in that problem, the pressure wasn't changing. So P1 and T1, or P1 and T2 are the same. And the number of moles was not effectively changing, so N1 and N2 are the same. And you're left with Charles now. Okay.
Is that the true combined version?
Yeah. So sometimes they leave the N1 and N2 off,
Yeah.
but that's the full one. And again, how did we get that? You take PV is equal to nRT. You solve for R. Move these N and T over the other side. You get PV over NT is equal to R. So the idea is, every time you put PV and T together, it's always equal to R. Always. So I could put any set of any gas at any state. And so P1, V1, N1, T1 is equal to another state, P2, V2, N2, T2.
Of the same thing?
It's got to be this for the problem, same problem, yeah.
Yeah. So like the same variables equal the same for the final and initial.
Well, the same
Always.
units. It's got it. Well, it's for the same system. That's the word I'm looking for. So you're starting with a gas at one state, and you're changing that gas to another state. And whether you add more moles, you change its temperature, you change the volume, or you change the pressure, it's got to be for that same system, that same gas. But yeah, this is always true for a gas that you're changing the state of.
So so I missed what you said about, so we're not going to have that, we just need to.
I'm going to try to put this on the exam. I need to remember to do that. I already wrote myself can do it. But I will put that in there. Okay. Let's see, what's next? Oh. Yeah, so 31 is one where you're going to want to use this. And when you do this, well, let's read the problem real quick. You have a gas, it's at 25 degrees, 1 atmosphere pressure, 2.5 liter container, and we change its state. It's now at a new pressure, a new temperature, and it's expanded. What is the new volume? So read the question carefully. You'll see that we're not adding or subtracting any gas, so the number of moles stays the same. So we can cancel out the moles part. And we're solving for V2. So I'm going to isolate V2. I want to get rid of P2 and T2. I'm going to divide by P2 on both sides. And I want to multiply by T2 on both sides. And notice that that cancels. So I'm left with V2 is P1 V1 T2 over T1 P2. And if you hate the algebra like that, feel free to plug in the numbers directly into this equation, multiply everything out, and then do your transformation. Sometimes that's easier for people, which is fine. They don't like moving like 5 different variables around. It's okay. So there it is. Now we just need to make sure we plug in the right numbers. So pressure 1 is 1 atmosphere. And we'll leave the units off because it's going to get messy. Volume 1 is a 2.5 liter container. Temperature 2 is 15 degrees C. But Kelvin, must be in Kelvin. So 15 plus 273. I should be able to do it in my head, but I want to. 288 Kelvin. Temperature 2 is 25 degrees C, so 298. And P2, so temperature 1, excuse me, is 25 degrees C. P2 is 0.85. Please don't feel like you should do it like I'm doing. Sometimes it's helpful to label everything before you start. That's V1, that's T1, that's P1. Make sure you label it so you know, oh, I'm plugging in the right things.
Really, you want us to use 273.15 on the exam, or just 273?
So I'm taking a shortcut because there's no decimals. If there is a decimal, then you should use the full conversion. But if there's no decimals, then 273 is fine. Because it's going to be 0.15, it'll round to nothing. Yeah. And it should be small enough that sig fig errors, rounding errors, wouldn't matter so much. At least not for multiple choice. Okay. 1 times 2.5 times 288, divide by 298, divide by 0.85. 2.8 liters. We started with liters, we'll end with liters. These are a little bit harder to check your work when you have multiple things changing. But it kind of makes sense. So that's good enough for me. So 32 is the different kind of gas problem. Instead of changing state, so the gas's pressure is changing or the temperature is changing, nothing like that is changing. We just have a gas. We have 3 of the variables, 3 of the properties, volume, temperature, and pressure, and we're being asked to calculate the 4th, the amounts, the number of moles. So we're going to be using PV equals nRT for that one. And PV equals nRT has restrictions. You must use atmospheres, you must use liters, you must use Kelvin, because R has those units in them. So we're going to solve for N. No. Yeah, moles. And I'm going to rearrange things. It's PV over RT. So pressure has to be in atmospheres. So let's quickly calculate it. Let's do it down here. 367 millimeters of mercury, or torr, same thing. There's 760 millimeters of mercury, and you can look that up in the conversion, in 1 atmosphere. So 367 divided by 760, 0.483. We'll convert the temperature while we're at it. 31 degrees is 304 Kelvin. So let's plug everything in. Pressure, 0.483 atmospheres. Volume 60.82. R, this is the one that has liters and atmospheres in it, so 0.08206. Liters times atmospheres divided by moles divided by Kelvin. And then finally, the temperature, 304. And I think it's A. I don't want to do it, but I think it's 1.18. Let's do it. 0.483 times 60.82 divided by 0.08206 divided by 304. Yeah, 1.18. So think about that. Approximately 1 mole of gas at a low pressure than normal, slightly higher than room temperature, is going to occupy a huge volume, 60 liters. Yeah, it makes sense. Remember the molar volume. The molar volume, 24 liters. That's when you're at standard pressure and standard temperature. So this is not standard. 33 is great because we're doing standard temperature. Okay. So this looks like it would throw some of you off at first glance. But think about what you can calculate. So we want to get molar mass. And somehow we're given the mass of a gas. Well, molar mass is mass over moles, grams over moles. So if I somehow got the moles, I could divide mass by moles and get molar mass. So there it is. I want to find moles. How do I get moles? Well, gas laws. I could use PV equals nRT to do it. But let's take the shortcut. Let's use molar volume.
Can you use the density one?
Well, you
No, actually,
can't
I just
use.
want density.
I mean, you could calculate the density. It's a mass that's occupying 1 liter of space. Oh yeah, you could do that. Sure. Oh, that's another way to do it. So I'll do that way in a second. So you could use molar volume. You could say, well, if I have 1 liter and it's at STP, well, that means that 1 mole of a gas will occupy 22.42 liters of space. That's the shortcut STP that molar volume tells us. So 1 liter of gas means I have 0.0446 moles of gas. Now that I have the moles, let's take the mass, 5.75 grams. Let's divide it by the moles, 0.0446. And notice you'll get grams per mole. That's molar mass. It's 129 grams per mole. Done. I could have not done this. I could have used PV equals nRT and plugged in standard pressure, 1 atmosphere, plugged in standard temperature, 273 Kelvin, and calculated that way. Dima mentioned, well, what about the density equation? Well, what about that one? So let me remind you that there's a version of the gas equation that has density in it. D is equal to P molar mass, that's what the M is in here, over RT. So what if I rearrange this to solve for molar mass? Yeah? dRT over P is equal to molar mass. I did that very quickly. So that's just algebra. But there it is. That's how I get molar mass directly. So plug in density. Well, how do I get density? Let's go back to the problem.
Mass over volume.
There you go, mass over volume, which we've got. So we've got a mass. It's, where is it? Yep. Further along. 5.75 grams over a volume, 1 liter. There's your density. Okay. Then we've got R, 0.08206. Temperature, standard temperature is 273. 0.15. And then P, standard pressure, 1 atmosphere.
that should give us the same answer, molar mass. Excellent. I hadn't thought of that one. But yeah. This one seems a little more complicated though. But yeah, it works.
That was the equation that you put on the answer.
Oh, is it? Okay. I'm gonna be honest. We share. The instructors share these practice stuff sometimes, so I didn't write some of those answers. I think this is easier, but it's up to you. Like I said, gas laws. There's usually multiple ways to solve stuff. Okay. 34. A flask contains helium and neon at a total pressure of that 2.6 atmospheres. There's 2 moles of helium and 5 moles of neon. The partial pressure of helium is what? So, partial pressures are also, there's usually multiple routes. So I just want to remind you that when you're thinking about partial pressure, the way you would calculate a partial pressure is exactly the way you calculate a regular pressure. So you plug in moles, you plug in volume, plug in temperature, you'll get a pressure. If it's only a portion of the moles of a gas, so like just like here, just the helium of your total moles, then you'll get the partial pressure of just the helium. But in order to use this equation, you need temperature, you need the rest of the variables, which we do not have. So we need an alternative, and that is using mole fraction. So the partial pressure of a helium is going to be the total pressure times the mole fraction of helium. So how do we get mole fraction of helium? Mole fraction of helium is the number of moles of helium, 2 moles, divided by the total number of moles. So 2 and 5 is 7. And that's a weird fraction. So calculation 2 divided by 7 is 0.285 or 0.286. You round it. Unitless. Mole fraction is unitless because the moles cancel. So total pressure, 2.6 atmospheres. Here, partial pressure of helium. Times the mole fraction of helium, 286, or 0.28, excuse me, 0.286 times 2.6 is 0.74 atmospheres. There it is. Whew. Okay. And you can get the partial pressure of neon instantly. You don't have to go through all that. There's just 2 of those gases, so if I subtract the partial pressure from the total pressure, I'll get the pressure of the neon instead, because they have to add up to the total. Anyway, that's not part of the problem, though. So, an ideal gas differs from a real gas in that the molecules have no attraction for one another. There it is. That's the answer. Ideal gases have no attraction, no IMFs, and they have no volume. They don't take up any room. And that's it. Everything else is not true or the opposite. All right, let's skip 36. That one's similar to the one we just did, and we're going to run out of time soon. So 37, when gases are treated as real via the use of the van der Waals equation, I think it's van der Waals technically, but whatever. The actual volume occupied by gas molecules will do what to the pressure exerted? And the attractive forces between the gas molecules will do what to the pressure exerted as compared to an ideal gas? So the volume that they take up, if there's less, like if you put gases in a container and you shrink the volume, what happens? The pressure goes up, right? So suddenly you're treating them as real. They actually take up more room than you thought they did. There's less space now. The pressure is going to go up. So the pressure will increase if you start treating the gas molecules as real because of their volume. But the attractive forces reduces collisions, right? So the more attractive the gas molecules are with each other, the fewer the collisions with the walls of the container. So there's a balance going on, okay? So the volume that they cup increase the pressure, and the attractive forces decrease the pressure. And that's why we saw that last graph that we kind of said we're not going to worry too much about, where it went down and then went up. Deviates negative and then deviates positive. But that's the explanation here. All right. I think we're going to skip 38 as well. This is just PV equals nRT. You're asked to find the volume of this amount, which you can turn into moles, at this temperature and that pressure. So you're finding the missing variable, PV equals nRT. Okay, 39. Manometers.
Just trying to trick us.
Am I trying to trick you? With what, manometers? Okay.
No, this question was,
It was hard?
well, it was just one that gave more information than was.
Oh, this one. Yeah. You're right. This one is a trick. Yeah. You're right. So, a closed-end manometer versus an open-end manometer. There's a difference. In a closed-end manometer, there is nothing pushing back on the gas. The atmosphere is not involved at all. And so the height difference that you read in the closed-end manometer is literally the pressure of the gas. That's it. So if the manometer reads 12.2 centimeters, that's 122 millimeters. That's the pressure. Case closed. Done. So A. Now, if it's an open-ended manometer, then it's a tug of war, or the opposite of tug of war. They're pushing each other between the atmosphere and the pressure of the gas container. So then you have to measure the difference in height and either add or subtract from the atmospheric pressure. Right? So if the gas pressure is pushing harder, you add to the atmospheric pressure. If the atmosphere is pushing harder, you subtract from the atmospheric pressure to find the pressure of the gas. Okay? Okay, but this one is a closed-ended. So that's it. Hey, done. This is not needed at all.
Can you repeat that again? About the height, the level?
Yeah, okay. I'll just do a little drawing too. So for an open-ended manometer, let's see if I can draw it properly. So this is open, and there's atmosphere pushing against here. If the height difference is like that, then the atmosphere is pushing harder, meaning the pressure of the atmosphere is higher. So the pressure in here is going to be whatever the atmospheric pressure is minus this height difference. If it's the other way around, if the mercury level is lower here, higher here, then the pressure in here is higher than the atmospheric pressure. And so the way you would calculate what the pressure is in here is you would take the atmospheric pressure and you would add the height difference if it was the other way around. So those are the two scenarios for an open-ended manometer, which is what this is. Which is a guess. Okay. 40 is another change of state, which is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. But you would cancel N in this case because it's not changing. And you would cancel volume because the volume's not changing. Yeah, okay. 41.
Can you do this one?
Do you want me to do? Okay, I can do that. Oh yeah. Okay, it's more algebra. Okay, so 41 is kind of an algebraic solution rather than what is the answer? So we have a sample of gas. It's in a volume of 15 liters. If we increase the temperature from 100 to 150, the ratio of the final to initial pressure is blank. All you got to do here P1 V1 over N1 T1, P2 V2 over N2 T2. First, let's simplify this. So number of moles isn't changing, so we'll get rid of the moles. And the volume isn't changing, so we can actually get rid of the volume. So it's just P1 over T1 is equal to P2 over T2. And then we are calculating the ratio of final to initial. And mathematically, that is P2 over P1. That's what we want. That's the ratio, P2 over P1. So I'm going to rearrange this to give me P2 over P1. I'm going to put P1 over down here. I'm going to put P2 over here. So far, so good? This is what we're trying to solve. This is a ratio. And so to solve this ratio, I just need to plug in T2 over T1.
Why did you?
What-
Sorry, can you repeat why you like made it from P1 over T1 to?
So
Oh,
the-
I guess it doesn't matter.
we want a ratio of final to initial pressure, and mathematically that's doing a fraction, like final P2 over initial P1. So I want to plug in T2 over T1, and the mistake people will make is plug in the temperatures directly, but we need to convert them to Kelvin first. So 150 C plus 273 becomes 423 Kelvin. And then 100 C to 273 becomes 373 Kelvin. So let's plug in T2 is, it's increasing, so T2 is 423. And T1 is 373. And that ratio is 423 over 373. 1.13. So that's the ratio. That basically, the idea is if I increase the temperature, how is the pressure changing? Well, the pressure is only going up by 13%. That's kind of what that means. So not much of a change. So the ratio, so this is the temperature change, T2 over T1, and it's equal to the P2 over P1, the pressure change, the pressure ratio. And that pressure ratio is 1.13 to 1. So a 13% increase in pressure is how you would read that.
So we don't even use
The volume is not necessary. Yep.
or the moles.
Yeah. It's not necessary.
Are we
Yeah.
going to be asked one like this?
It's possible. I'm not going to say yes or no, but it's possible. I prefer not to give you math ability questions, like this is more mathematical thinking, but I can't say no, but less likely to that. Okay. All right.
There's no unit with that, or would that be Kelvin?
No, there's no unit because the kelvins cancel out. And so it's just a ratio. So how much would it increase? It went from 1 to 1.13, or so 1.13 times. That's how much it increased by. That's what the ratio tells you. So if the pressure started out at, and you could calculate it. Maybe that's so. One of the reasons they give you the moles and the volume is you can literally calculate your starting pressure, and then you can calculate the new pressure. And then you could do the ratio that way. So there is a different way to do it, I guess. It's longer. This is easier. Okay. Gases and liquids. The big difference here is a gas always assumes the volume of its container. Assumes the shape of the container. Same thing. So if I put a liter of soda into a 2-liter bottle, it's not going to fill the 2-liter bottle. It's going to be a liter. Whereas if I put a liter of air into a 2-liter bottle, it will expand to fill the 2 liters. It becomes 2 liters. What statement about atmospheric pressure is false? The C is false. With an increase in altitude, the atmospheric pressure increases? No, it decreases. The higher you are, the less air there is on top of you, so the less pressure, the less weight of air there is. All right, so
The higher you are, there's less pressure.
yeah. The high, you're on a mountain. There's such low pressure that you need special breathing apparatus to breathe. So 44, I can skip this. I think you can look it up. PV is a constant. It's A. Charles's law. It's B. Which of the following is a valid statement of Avogadro's law? That's volume in moles. So D. Okay, we got through most of those. So let's get to the short answer questions now. And we have vapor pressure curves. So these are described with the Clausius-Clapeyron equation, the other form that we don't ever use. They're curved like that, but that's when you plot temperature and vapor pressure directly. But you still need to be able to read these. What is the vapor pressure of heptane at 70 degrees C? There's heptane at 70 degrees C. The vapor pressure is 300 millimeters of mercury. What is the normal boiling point? So for boiling point, you look up what the vapor pressure is going to be. You look at what temperature will the vapor pressure equal the atmospheric pressure. So 760 is our atmospheric pressure. So for ethanol, that's right around here, 760. You go down right around 78 degrees. Try to be somewhat accurate, but you don't have to be perfect. It's fine. What type of intermolecular forces exist between two CS2 molecules? So again, you're going to have to learn how to draw your Lewis structures if you haven't remembered how to do it. CS2 is actually exactly the same structure as CO2. One clue is that O and S are in the same valence group, same group number. So they're the same number of electrons. So they'll end up the same shape as this. CS2 looks like this. I didn't draw the lone pairs on the other one, but that's what it looks like. This is nonpolar. I mean, it's got polar bonds in it, but they cancel each other out. There's no negative or positive side to this molecule. So if it's nonpolar, dispersion forces, that's it. Heptane, dispersion forces, that's it. It's an alkane. But ethanol, OL, that should be, well, it's even drawn up there. The OH, I guess CS2 was in the little chart. There's a giveaway right there. But it doesn't show the lone pairs. You have to remember that carbon only has 4 bonds, so there's the 4. But anyway, ethanol has the OH, so hydrogen bonding. But also dispersion forces. Don't forget that.
So we write both.
Should, yeah. What type of intermolecular forces exists? I guess that seems like singular, but the way it's written, it should be 2, yeah.
And you said heptane is dispersional.
Mm-hmm. By the way, if these questions are flawed, that's the reason they're on the practice test. They were taken out of a regular test. So, suppose the pressure is 600 millimeters of mercury and the temperature is 50. Decide if each substance is a liquid or vapor. So, you're just going to have to look and see, are we above the boiling point? So the pressure, the current atmospheric pressure, whether it's in real life, that's what we're existing, it's on a mountain, or artificially inside a sealed container. 600 millimeters of mercury, is it boiling at 50 degrees? So carbon disulfide at 600 is boiling at 38, 39. And so, yeah, it's a gas at 50 degrees. It's not a liquid anymore.
Well, how did you know
So-
that? Because it doesn't mark like.
Yeah, so carbon disulfide at 600 millimeters of mercury. There's carbon disulfide. And 600 millimeters of mercury is right here. And if I go over that at 38 degrees or 39 degrees or so, that's when the vapor pressure of carbon disulfide reaches the external pressure of 600 millimeters of mercury. So basically, it's already boiling above 38. So the normal boiling point, all right, is when the vapor pressure matches the atmospheric pressure. So the normal boiling point of carbon disulfide, 760, is 46, 47 degrees, okay? But that's under, like if I have a vial of this out on the bench top and it's regular pressure. If I put a vial of this carbon disulfide in a container and artificially lower the pressure inside that container to 600 millimeters of mercury, well now, at 600 millimeters of mercury, this stuff will boil at 38 degrees.
And you
And then the idea is, well, okay, let's say the conditions are that, but the temperature is 50 degrees. Is this stuff going to be a liquid or a gas? Well, it's past the boiling point, so it's got to be a gas now.
And you said so the normal boiling point is at 100 degrees. I mean, is 100 atmosphere.
Is that 1 atmosphere?
Is that
So 760 millimeters of mercury. It's right around here. The normal boiling point of carbon disulfide would be around 46, 47 degrees.
and it's less than that. But wait,
Well, so now we've artificially lowered the pressure.
Yeah.
Like just like water boils at a lower temperature when you're on a mountain. Carbon disulfide will boil at a lower temperature when you lower the pressure too. So at 50 degrees, if I artificially heat this stuff up to 50 degrees, I've gone past its boiling point, and so now my carbon disulfide is a gas. So for ethanol, right, ethanol's normal boiling point is 78 degrees. If I make the pressure lower, ethanol's boiling point is now 73, 72 degrees. So at 50 degrees, this stuff is still going to be a liquid. Okay? And heptane, still a liquid. Which one of these can you expect to dissolve in water? Ethanol. Similar IMFs will dissolve in a substance with similar IMFs. So, only ethanol has hydrogen bonding. Why is the normal boiling point of ethanol higher than that of CS2? Hydrogen bonding, stronger IMFs. Why is the normal boiling point of heptane higher than CS2? More dispersion forces. In this case, more surface area. So more possibilities to do dispersion forces, more interactions possible. You could just go straight to molecular weight probably though. Although I don't know if that would help in this case. C7, 12 times 7, 72, no, 84 plus 16. Yeah, it's a little bit higher at molecular weight, but not by much. All right. Here we've got phase diagram. What is the normal boiling point? But the clock had broken for a second. Yeah, that's where C is, sort of. So it's 78 degrees. It's kind of hard to, it's not really a good scale here to judge it by, but it's around 80 degrees. What is the normal freezing point? So at 1 atmosphere, the solid liquid boundary is right here. It's like just above 5.5. 7 something, I don't know, 8, 10. It's hard to gauge. It's where B is, let's put it that way. Which letter corresponds to the critical point? That's D. Triple point. That's A. Sublimation occurs at what pressures? Sublimation is solid to gas, solid to vapor. It can only occur along this line here. the solid to vapor transition. So it has to be below 0.5 atmospheres for it to occur. And that is 4, below less than 0.5 atmospheres. If you're on the exam and you have no idea what the symbol less than or greater than, you forgot which one is which, let me know. I will try to remind you. Skip a F. This is something we haven't talked about. This is related to that last question. Vapor pressure and phase diagrams. We're not going to talk about that right now. So we didn't talk about it at all. And 49. This is a hard question to answer very accurately, but that's not really the point. It's just making you think of what's happening. So ethanol and water, you have 50 mils of each. You mix them together, suddenly it's less than 100 mils. Like you should be adding them together, and they should add together properly. So what's happening is somehow the interactions between ethanol and ethanol create certain spaces between the molecules. The molecules have to have a certain distance between them, and there has to be a certain amount of empty space to create a certain density. And that makes it that volume. Water does the same thing. Water interacts with water, and it has certain distances it has to have, right? We've kind of seen that water has to be oriented a certain way, right? The positive end has to be pointed to the negative end. You can't have negative and negative touching. You can't have positive with positive. So the way they interact with each other, there has to be lots of empty space or certain amounts of space between them. But if you mix these two together and suddenly it's less volume than you'd expect, it must mean the two different molecules are interacting with each other and taking up less space as a result. Somehow they pack together a little bit more tightly. That's all. It's nothing's very specific. It's a vague answer, but that's what must be happening. So we just ask you to think what's happening at the molecular level that would cause this to happen. And that's not a good test question, by the way. It's just more of a lab question. But this is a good test question. Why does water boil at a lower temperature up in the mountains versus at sea level?
Atmospheric pressure is lower.
Yes.
It's lower.
So, but why does having lower atmospheric pressure lower the boiling point?
There are less forces down on the water, and the vapor pressure of the water is decreased. So they're easier to break free of the liquid.
Yeah, pretty much. I think I understood what you said. Were you going to say something similar?
I didn't quite catch it. But because if the atmospheric pressure is lower and boiling point is when the pressure of the liquid equals the atmospheric pressure, so that if it's lower, then it'll boil at a lower temperature.
Yeah. So that's exactly true, but it's still not getting into the molecular reason. So how is a lower atmospheric pressure? And what she said I think I got it. I think what you said was right. So think about why certain molecules evaporate. It's because suddenly they have enough energy, and if they're near the surface, they have enough energy to break the intermolecular forces and fly away. But if you've got air molecules slamming down on them, some of them might keep those molecules, the liquid molecules, as a liquid, prevent those from flying off as a vapor. So the fewer air molecules you have slamming down on the surface, the more likely those liquid molecules are then able to escape. So that's kind of the molecular reason.
So you said there's less molecules pressing down. So wait, you said there's more, so it's easier for them to
So,
escape?
all right, so you've got a liquid, okay, and here's your liquid molecules, and some of these molecules have enough energy to escape, and they turn into a gas. But let's say you've got only a little bit of air. Well, these molecules are also slamming into the liquid, and if there's not many molecules, then these not many air molecules, these liquid molecules have an easy chance to escape. There's nothing interfering with them escaping. But let's say that there's a ton of air, higher pressure. Well, now there's more air molecules slamming into the surface of your water. kind of getting in the way of these liquid molecules escaping. So that's kind of the molecular reason why a higher pressure, atmospheric pressure, causes the boiling point to, well, actually,
There's like more.
I think I'm talking about something else. Hold on a second. We're talking about boiling point. So,
The boiling point is lower because there's more, like,
I mean,
air
I-
pressure pushing down on it.
it's still the same reason. But all right, this is not a great question. This is what like I said, it's another lab question. It's a combination of what I said, but it's a combination of what you said. It's an equilibrium thing. Let's move on because this is not helpful for the exam. All right. Which of the following compounds would be expected to form IMF, intermolecular hydrogen bonds, with water? This is not the best question either, but I think the answer and the key states that all of them except for propane can do it. And the reason for that is the water is the thing that is providing the hydrogen bonding. Okay, it's got the OH bonds in it that are very, very polar, and that is what is doing the main interaction. And it doesn't matter that it's the other thing it's interacting with has hydrogen bonds or not. As long as the other thing has something it can interact with, then we would say that it can do hydrogen bonds with water. You might have seen on the slides that we've shown interactions, hydrogen bonding with other molecules. And sometimes we showed like carboxylic acids, something like this. And this is the part that does hydrogen bonding. There's the OH in there. It's a very strong dipole moment. There's a partial positive, partial negative. This doesn't have to interact with another OH. It can interact with a dipole too. And so this thing, oops. Can interact with this because that's a partial negative as well. And that's what we're talking about here. That this, in this case, it's water. The hydrogen bonding that water does can interact with anything that's polar. And I don't like this question that much because dimethyl ether, while technically that has a dipole moment, it's pretty weak, and it really doesn't interact with water very well at all. I would say that in real life, we would not say that they interact at all. They don't mix very well. But definitely this, definitely that, or definitely that. Definitely not propane. Propane is completely nonpolar. It only does dispersion forces. It's the wrong kind of IMFs to interact with water. Diethyl ether is borderline, which is why I'm not a fan of the question. Because I will give you clear, hey, this works, this doesn't. All right. These questions are great because this is the kind of question I could ask you to explain with words, not just pick a box. Use the kinetic molecular theory to describe what happens to the pressure of a gas when the volume is decreased and the temperature and the number of moles are held constant. So we are talking about Boyle's law here, but you can't just say Boyle's law when pressure goes up, volume goes down. You have to explain at the molecular level what's happening. So when the volume is decreased, the gas particles, which have the same average kinetic energy as before, the temperature is not changing. So the kinetic energy is not changing. The speed, the average speed is not changing. Well, now in a smaller volume, if you go to a smaller volume, these gas particles have less distance to travel. And so there's going to be more frequent collisions with the container walls. And more frequent collisions creates a higher pressure. So a smaller volume creates more collisions because the gas molecules are going the same speed or same average speed. And so you'll have a higher pressure from the increased collisions. So when we talk about pressure at the molecular level, you have to describe frequency of collisions and the strength of the collisions, the force. How hard do they hit? So that, how does, what affects that? Their mass, the higher the mass, the harder they hit. The faster they go, the harder they hit. So the higher the kinetic energy, okay? So both of those things, frequency of collisions and force of collisions, will affect pressure. But in this case, it's just frequency. Sorry, 52 is frequency. I think we can skip this one. This is just partial pressures, similar to what we did before. You've got 3 different gases. You've got a total pressure. We're going to do mole fraction. Mole fraction times the total pressure gives you the partial pressure. Done. So the 25 degrees is useless there. You don't need it. Oh, well, that's it. So maybe we should do that one. Or we could stop. Do you want to do that one real quick or no?
Yes.
Yes, okay. No problem. So, partial pressure of each gas. Calculate the volume of the flask. So, let's do that first. How do I do the volume? Well, it's going to be PV equals nRT. And I've got a total pressure. So if I plug in a total pressure and I want to find a volume, I need to make sure that the number of moles is the total number of moles. Right? Those have to match. But temperature and volume is going to be the same for any scenario, or any of these, I should say, this scenario. So total pressure, no, volume, not total pressure. Volume is going to be number of moles total times R over times T divided by total pressure. And so the total number of moles, I just add them all up, 0.4, 0.6, and 1.5 is 2.5 moles. R is 0.08206. The temperature, 25 degrees C, so 298 Kelvin. I'm converting these quickly, sorry. And pressure, total pressure is 1.8. So the volume is 2.5 times 0.206 times 298 divided by 1.8, 33, so 34.0. Okay, so there's your total volume. Now, you can do the second part any way. There's 2 ways to do it. You can find the pressure, partial pressure of oxygen by using the number of moles of oxygen and then RT over V. That's one way to do it. You could have to do it for all 3 gases the same way. Or you can find the partial pressure of oxygen by getting the mole fraction of oxygen multiplied by the total pressure. These are the 2 different ways to do it. So it's up to you which one seems easier. I think the mole fraction one is easier. So let's do the mole fraction one. Less calculation. So the mole fraction of oxygen is 0.4 divided by the total moles, 2.5. And that's 0.4 divided by 2.5. Oh, that's not right. Divided by 2.5. 0.16. And so the mole fraction of, the partial pressure of oxygen is mole fraction 0.16 times total pressure 1.8. And so the partial pressure is 0.288, so 0.29. Just going to round it really briefly. Keep going. Partial pressure of nitrogen is 0.6 over 2.5, 0.24. And then the partial pressure of nitrogen is 0.24 times the total pressure, 1.8, which happens to be 0.43 atmospheres. Okay. You can do the last one exactly the same way. Mole fraction of hydrogen, get the partial pressure of hydrogen, or the partial pressure of hydrogen is going to be the total pressure minus the partial pressure of oxygen minus the partial pressure of nitrogen. Why not? Because they all have to add up to the total pressure, right? So I just move things around. So 1.8 minus 0.29 minus 0.43 is 1.08. There we go. Those are the three. You definitely could have done partial pressure of hydrogen the same way as you did these three, though. Any way works. Or you could have skipped all this and just done this for 3 times, and then done. So, once you have a bunch of variables, you can do whatever you like. It's when you're missing stuff that you have to kind of limit what you can do. Okay. You guys are all ready, right? All ready. All right. So, see you guys on Thursday.